sklearn, impute, iterative imputer. Description. Iterative imputer is a sophisticated imputation technique in scikit-learn used to handle missing values in datasets. It works by iteratively predicting the missing values in each feature based on the other features in the dataset. This approach is particularly beneficial when dealing with complex relationships between features, where simple methods like mean or median imputation might not be sufficient. Inputs. X the input dataset with missing values. This should be a 2D array-like structure. Estimator the estimator used to predict missing values. This can be any estimator that supports the fit and predict methods. Common choices include decision tree regressor, Bayesian ridge, linear regression. Missing values, the value that represents missing values in the input dataset. By default, this is set to none, not a number. Sample posterior. This parameter controls how the imputer handles the uncertainty in pay predictions. If set to true, it will sample from the posterior distribution of the estimator to generate imputed values. This introduces more randomness into the imputation process and can be helpful in capturing pay uncertainty associated with the missing values. If set to false, it will use the predicted mean from the estimator as the imputed value. Outputs. Zimputed, a transformed version of the input dataset where the missing values have been replaced with imputed values. Steps. Initialization. The imputer initializes a temporary copy of the input dataset with missing values. Iterative imputation. The imputation process proceeds in a loop, iterating through each feature with missing values. For each feature, the imputer selects all other features without missing values as predictors. The estimator, e.g., decision tree regressor, Bayesian ridge, is fit on the available data. The fitted estimator is used to predict the missing values in the current feature. The predicted values are used to replace the missing values in the temporary dataset. Convergence. The iterative process continues until a specified convergence criterion is met. This criterion could be based on the number of iterations or the change in imputed values between iterations. Metrics. Mean absolute error measures the average absolute difference between the imputed values and the true values if available. Root mean squared error RMSE measures the average squared difference between the imputed values and the true values. Visualization plots. Scatterplots to visually assess the relationship between the imputed values and the original values for each feature. Histograms to examine the distribution of the imputed values for each feature. Fine-tune parameters. Estimator. Different estimators, e.g., decision tree regressor, Bayesian ridge, can be chosen to suit the nature of the data and the relationships between features. Maxiter. The maximum number of iterations the imputer will perform. Random state sets a seed for the random number generator used in the imputer. This ensures reproducible results. Uncertainty methods. Sample posterior true. This method introduces randomness into the imputation process by sampling from the posterior distribution of the estimator. This captures the uncertainty associated with the missing values, resulting in more realistic imputed values. Predicted mean. Sample posterior false. This method uses the predicted mean from the estimator as the imputed value, providing a deterministic imputation approach. Challenges and fixes. Challenge 1. Overfitting to the training data. Sample use case that resulted in challenge 1 using a highly complex estimator like a deep neural network for imputation when the dataset is relatively small or the relationships between features are nonlinear. Fixes to challenge 1. Regularization. Adding regularization techniques like L1 or L2 penalties to the estimator can help prevent overfitting. Early stopping. Implementing early stopping during the training process can prevent the estimator from learning too much from the training data. Cross-validation. Using cross-validation to evaluate the performance of the imputation model on unseen data can help identify overfitting. Challenge 2. Computational cost. Sample use case that resulted in challenge 2. Imputing a large dataset with many missing values. Using a complex estimator and a large number of iterations. Fixes to challenge 2. Feature selection. Selecting only the most relevant features for imputation can reduce the computational complexity. Reducing iterations. Lowering the number of iterations maxiter can decrease computational time without sacrificing imputation accuracy. Choosing simpler estimators. Using simpler estimators like linear regression or decision trees can reduce the computational burden. Parallel processing if possible. Leveraging parallel processing or distributed computing can accelerate the imputation process.